You have stuff for me. Step 3. I mentioned modes and what we did when we had multiple modes, and I said there was a different Excel command you could use for mode. There's mode singular and mode multiple. When you do a multiple mode, you only have to enter it once. So here, the pile of data about the state civil service exam and a bunch of scores. 24 different applicants. And I'd like to know if this data has a mode, but I don't know if it's only going to have one or if it's going to have more. If I use the multiple command anywhere in here equals mode, I start typing the word mode and the two options come up. The top option is multiple, so .mult parenthesis, then I need to tell it where the data is. So I go highlight my data. And as soon as I tell it to give me the mode, watch what happens. It produces two values. And that tells me this is bimodal data. So even though I only issued the command once, I got both answers in the same setting. I also previously down here had done the mean and the median and the modes, and my histogram down here. This histogram is set up by tens. By tens, I don't really see the bimodal nature because it's kind of jammed together up here. And my two modes, one was 80, one was in the 80s, one was in the 90s. So having this tie, where's my picture? There, that makes sense. Is this data lopsided? Is it skewed? No worries. I guess it will be there as well. Is this data skewed? Which way, Helen? Ah, I have that one pair over there. But let's go back and look at the numbers. How can I tell about that skew from up here? With the mean, the median, the modes, with my measurements of center, what up there tells me about the skew? We had pictures at the end of class on Wednesday. Okay. Emily?
So, like, because the mean has the most frequency, so you're gonna have for the mode.
Right.
Yeah.
But we don't know how many it occurred, right? We don't know if that 82 occurred twice or 3 times or 7 times, right? I can't tell just from the mode that those are the highest. As a matter of fact, if we actually look at the sorted data, I see that 82 occurs 3 times and 93 occurs 3 times. But the fact that there are 24 pieces of data here, 3 out of 20, that isn't a huge piece, right? What about the other numbers up there? Tell me about skew.
And it's in the middle, so you know if the value's higher than
Hmm. The statement you made, the median is right in the middle. Half the data is above the median, half the data is below the median. That's perfect. But the average is a measure of weight, right? So the average tells me where more stuff is. The average here is lower than the 50% mark. So more weight is below the middle than above. Bottom of page 102, we see these pictures. My data is skewed left when the mean is lower than the median, to the left of the median. My data is skewed right when the mean is to the right of the median. That's the direction of the tail. It tells me more stuff is out in this direction, further away from the big mass. Remember, the mean is more sensitive to those extreme values. So when I have an extremely high value, it pulls the mean up higher than the 50% mark. So the fact that my mean was lower than my median tells me, oh, there must be something on the low end pulling the mean down to make my skew go off to the left. So that's how I can determine more about shape from just these measurements of center alone. Questions? Okay. There are a couple more measures of center that are a little less common or used in more specific areas. We've called the average the mean, right? But I actually gave it another word. I called it something, a specific kind of mean. Yeah, Wednesday. Arithmetic. Arithmetic means adding. Because we added all the numbers and then divided by how many there were. Well, what if instead of adding, I did something else? Well, subtracting isn't any really different than adding. It's just adding with negatives in it. So what if I switch from adding to multiplying? Now, wait a second. If I multiply two numbers, I should not divide by how many there are to get back some sort of average. Two numbers, ready? 3 and 5. If I take their arithmetic mean, their average, 3 and 5 is 8, divide by that 2, I get 4, right? But 3 times 5 is, I'm going to divide, my average should be somewhere around 3 and 5, right? It should be up at 15. My arithmetic average was 4. All of a sudden, my brain goes, wait a minute. What's 4 squared? I'm multiplying. What's 4 times 4? Which is pretty damn close to 15, isn't it? So if I multiply the numbers together to unmultiply, I'll take a root. A geometric mean uses multiplying. What we do is we take the product of all of these numbers. And then I have to take a root, but not a square root. I have to take an nth root. So if I had 3 numbers, I'd take a third root. If I had 7 numbers, I'd take a 7th root. If I had 19 numbers, I take a 19th root. We often write the multiplication in a shorthand like we wrote our adding. What did I use to shorten up the adding of all of those numbers in the average? It was a symbol I used on Wednesday. That big capital Greek sigma, right? And it's an S for sum. What's the Greek letter for P? Oh, pi. We'll use a big capital letter P and take our index I, go from 1 to n. So this says keep sticking the numbers on and keep multiplying. Multiply the first number, multiply the second number, multiply the third, just multiply over and over. This is short for this multiplication. I still need the root though, right? Here's another sneaky thing from algebra. Roots are fractional powers. So a square root is a 1/2 power. A cube root is a 1/3 power. A 7th root is a 1/7 power. This is actually the way I want to do this on my calculator. If I have a bunch of numbers to do their geometric mean, I'm going to write this up. And I'm not actually going to look for a root button. I'm going to use this power instead. Now, the real question is why the hell would I do this? What sort of masochist came up with this idea? You go in to a store and they have a 10% sale going on right now. Everything in the store is 10% off. My object that was $100 is now $90. They get a call from corporate. Raise your prices by 10%. How much does that item cost? That would be original cost, right? But off the sale, if it's $90 and I get told to raise the price by 10%, what's my new price? What's 10% of $90? Be 9, so if I raise it, it'd be 99, right? Wait a second. I say take a 10% off and then put 10% back on. Did I end up back where I started? No. So what I really did was I took 1.1 and, sorry, that's putting the 10% back on. I took 0.9, multiplied, and got my actual value, didn't I? So when we think of percentages, growth, this is actually a better number. Business time, it's a business statistics course, right? I have a money market fund. For the past 5 years, the return on investment in the first year, my portfolio went up by 10%. In the second year, it went down 12%. In the third year, it went up 90%. In the fourth year, it went down 30%. And in the fifth year, it went up 25%. Question. I get audited by the government. The government says, you are advertising your average return for the past 5 years. And you're using the wrong number. What is the arithmetic mean of these numbers? What's the arithmetic mean here? Right. So the ad says, you say for the past 5 years, you've had a 16% return. And you want us to base your taxes off of that. But look at what happens if my money market account that followed these returns on investments had $1,000 in it. How would I figure out the value at the end of 5 years? I would take that $1,000 and I'd increase it by 10%, right? But then I'd decrease that amount by 12%. Wait a minute, isn't that multiplying, not adding? I would take my original value and I would add 10%. Multiply by 1.1. And then I would lose 12%. And then I would gain, with a really good year, 90%. And then I would lose 30%. And then I would gain 25%. If I am averaging by multiplying, I should not be using the average the way we just did. That 16.6 is way off. What's the value of my $1,000 the end of 5 years? Do this multiplication. I don't expect you to do it in your head.
Let's say minus 4 point. So
Here?
Yeah, 0.12.
Yeah, because it's 12%, right? So this is 1,000 times 1.1 times 0.88 times 1.9 times 0.7 times 1.25. What do you get? Okay. A question from your business algebra class. Time value of money, compound interest. Anybody know the formula for compound interest? BU 280, personal finance, next semester. Take that one. You'll learn this formula. The formula for compound interest is that your future value is equal to your present value one plus r raised to the t power, because you earn that interest by multiplying year after year after year, right? So if I want to know what the rate was, I know it was for 5 years. This is my future value, this 1609.30, and this is my present value over here. I actually need to solve that. Ready for the sneaky part? Take the numbers, this number. Let's divide by 1,000. you would get 1.6093, right? That's the same as if I divide this over here, isn't it? But this number is the same as if I multiplied all of those together without the 1,000, right? And then I'm taking a fifth root. To get rid of this fifth power, I get 1 plus r is the fifth root of 1.6093. Now, on your calculator, you should have a power button. You can raise directly to the 1/5 power on your calculator. So I'm going to do exactly this calculation. 1.6093 raised to the 1/5. I'm even typing it as a fraction. That number that we just got is the geometric mean of those underlined numbers. It's the average rate of return per year when you know the year-over-year returns. Which means I'm not actually charging 16, not earning 16 point, what was it, 16.6? I'm not earning 16.6. I'm really earning 9.98%. Copy the number down. So 1 plus r equals 1.0998 dot, 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 dot. R is 9.98%. Return on investment is a geometric calculation, not an arithmetic calculation. Growth rates, even when it's not money, when we talk about finances, that's a great example, but we can talk about population growth. We can talk about land growth by forests or land diminishment. I mean, these numbers are negative, right? If 1 plus r was less than 1, things would be shrinking. You lose money, you lose land area. We can talk about beach erosion, same idea, because that's a multiplication problem, not an adding, subtracting problem. Questions? Yes, sir.
Where 1 plus r equals
Uh-huh.
1.0998, and then
I subtracted the 1.
is that
I subtracted the 1 off, and then I moved the decimal place over to make it a percent. By the way, the reason this is called a geometric mean is because this idea really comes from something called the ratio of lengths of segments in a circle. It comes from Pythagoras in right triangles. So it really is a geometry idea at heart. The example I started with was 3 and 5, right? And the arithmetic mean was 4. What's the geometric mean of 3 and 5? I multiply them, and I take the 1/2 power, the square root. So the geometric mean would be the square root of 15. Somebody give me a decimal. Notice that the arithmetic mean is bigger. When we did the arithmetic mean of our other numbers, we got 16.5, right? And when I do the geometric mean, I get, oh, something smaller, 10. It turns out this is always true. The geometric mean is always smaller than the arithmetic mean. There's a really nice theorem in math called the arithmetic geometric mean theorem. Deals exactly with that. It's beyond the scope of this course, but I thought I'd mention it. So in business, the primary use of this is examining growth rates. And you'll notice how we did that subtracting 1, right? If you talk about year-over-year growth rate in general, you almost always subtract the 1. There's a formula in the textbook. Called growth rates, top of page 107. They're subtracting the 1 right there. Now notice they've got fractions involved here, right? But what they're thinking is growth year over year is a percentage change. So it's this year's over last year's. And when you stack all those fractions together, a bunch of the middle stuff cancels out. And you really only need the last number and the first number. That's why it's xn over x1 in this formula. And here's an example where they show me all of that canceling out on page 107. I like geometric means. I think they're a very interesting idea. This is really a very special use of the idea of center. Questions? Sometimes, especially in data that has outliers, it's not useful to use those outliers. When we're talking about home prices, really expensive homes, and the falling apart shack on the edge of town, they're going to skew the numbers a bit. So a lot of data throws out outliers. They trim them off. And quite literally, you could say, how big a slice of the data do you want to take off? And what we'll do is we'll create a trimmed mean. A trimmed mean does exactly that. It cuts off a certain percentage of the data. Now, I didn't actually pick a number, but if you were to say a 5% trim, well, then you'd want to trim away 5% of the data. But what I've written is I want you to trim away 5% at the top and 5% at the bottom, which means my total trim is 10%. So if I'm doing a 5% total, then I would have 2.5 at the top, 2.5 at the bottom, an 8% total, 4 at the top, 4 at the bottom. It's got to be symmetric. It's got to be the same percentage of numbers off the bottom and the top. By the way, let's say I had 53 numbers and I wanted a 5% trim. Sorry, a 10% trim. Means I want the bottom 5%. What's 5% of 53? Do not have to do this in your head. How do you trim off 2.6 numbers? So you trim off 2. Always round down when you are doing a trim. By the way, there's a command in Excel to do a trimmed mean. So something like, this one tight. This command, trim mean as one word, then you tell it where the data is, comma, the percentage for 2K. So this says 0.2, that's 20%. 20% means you take off the 10% on the bottom and the 10% on the top. A 20% total trim. Who's going to do something like this? The federal government. When you calculate consumer price index, you look at price changes in goods and services. So one of the things that is a big part of the consumer price index is changes in housing cost. How much has your rent gone up versus last year? They do this survey all over the place. Hundreds of different apartment complexes, hundreds of different neighborhoods countrywide. And then they say rent has gone up this much. But some cities have really big housing crunches. And some cities have really cheap housing. You can buy just about anything you want outside of Detroit, because half of the suburbs of Detroit are abandoned. You can buy a 6-bedroom house cheaper outside Detroit than you can buy a 2-bedroom house in Greensburg. On the other hand, you can't buy a squat in New York City right now. I watched a YouTube short, Instagram reel, I don't remember where. I was watching a social media video, and I saw a gentleman do a tour of a 2-bedroom, 3rd floor walk-up, 2-bedroom, 1-bath apartment in New York for $5,000 a month. I buy a 4-bedroom house in Greensburg for half that. And it comes with land, not a cube of space in the middle of a 3rd floor somewhere. So I take off the low end, I take off the high end. The consumer price index does have, I believe it is a 5% total trim in lots of different categories. When we do food as a category in the consumer price index, I'm measuring inflation on food. Can you imagine if eggs was part of that last year? Gasoline, fuel is a part of the consumer price index. I have to account for that fluctuation. So trim means show up a lot in places like that. One more measure of center is called the mid-range. The mid-range is quite literally halfway between the highest and lowest. I started to write this and I realized I was about to write it wrong. Nope, that's right. Plus over 2. It's literally take the lowest one and the highest one, split the difference. You want to talk about sensitive to extremes? It only looks at the 2 extremes. But in a sense, a mid-hinge tells me what I think, just looking at the extremes, the middle should be. And then the mean will tell me where more of things went. The median compared to the mid-range will tell me how the district, these give me more insight to shape than they do always to center. The JD Power file that we opened up last time, I went ahead and added all of the other pieces here. Tag says additional centers, geometric mean, mid-range, 5% trimmed mean. Wait a minute, that's a 5% on each end, so that's a 10% total. You will find different sources name the size of the trim differently. One textbook I saw said a 10% trim is 5 low, 5 high. Another textbook said a 5% trim is 5 low, 5 high. Be careful. That's why in our formula, we used the double because Excel splits it. It says if you want a 5% off the bottom and 5% off the top, you're taking away 10% total. Questions? When I talk about the variability of my data, I'm really talking about the spread. Do I look at data that's tightly clustered together, or do I look at data that's really spread out far? Spread is not always related to symmetry. You can have data that's really spread out and is still lopsided, or you can have data that's really spread out and is symmetric. In the middle of page 110 is this picture. What's interesting to me is that all three of these little dot plots have the same center. They're all centered at 4. Now, these happen to be symmetric. They're the same on the left as they are on the right. And the middle, the mean, the median, in all three of these is 4. The mode is not universally 4. The mode is 4 here. The mode is 4 here. The mode is not 4 here. This is bimodal data. But these are symmetric. I could still, if I moved one dot from 6 over to 2, that would be asymmetric. But it would still be a lot more spread out than this data, wouldn't it? Our measurement of spread is usually related to our choice of center. So which center we want to use helps us determine which measures of spread are most useful. The most common measure of spread is range. Hey, wait a minute. The measure of center that is sitting at the top of the screen right now says mid-range. What do you think the range is then? Give me some other than a gesture, Emily.
The X max minus the X min.
How far apart they are. Since the mid-range is the middle of that, that makes perfect sense to me. That's it. Now, it is also a very limited measure of spread. If I gave you an exam and then I came back and I said the range of scores on the exam was 40 points, does that tell you anything? Well, means the difference between the high score and the low score is 40 points. But are those 160 or are those 41 and 1? Ugh. I get information about spread, but I don't get any sort of target to it. So while it is useful, it is very limited because it really only depends on two values. Phooey. It's a really simple calculation. As my measures of center get larger and more complicated and more useful, so do my measures of spread. As my measures of center get more useful, more complicated, so do the corresponding measures of spread. So this is the simple, but it doesn't give me very much utility. If I want something that's more useful, the complication is going to show up in the calculation. We did average. We did arithmetic mean as my first measure of center. So let's start with the spread that goes with that. The variance and the standard deviation are calculated based off of the mean. Don't put that X down there, I apologize. It's just S squared. It's the sum xi minus x bar over n minus 1. What the bloody is going on here? Oh, I forgot something. See, there's a square on the left. I forgot the square on the right. And it's important because I was about to ask you, why is this squared? And if I don't have the square in there, then I can't ask you that question. Why is, all right, who the hell came up with this square item? X bar, that was our average, right? And that's our balance point based on where the distribution is, right? That's my fulcrum on my teeter-totter. That's where I put the balance. So xi minus x bar is how far away each weight is from the balance point, right? Do I want to think about negative distances?
Negative distances, but as a standard deviation in both directions.
It's got to go in both directions. So if I square stuff, then small things become even smaller and they're less important. Negative things become positive things. I don't have to worry about anything being negative here. And big things become even bigger things. So the things that are far away have more weight in my spread because I'm squaring. And things that are really close don't have a lot of effect because when you square a small number like a half, it gets smaller. A half squared is a quarter. Oh, by the way, if I got rid of the square and put absolute values there instead, that would be a different version. And that's called absolute deviation. You will barely ever see that. But there's another way to make these things all positive. Now, that's based on a sample, right? Because I've got X bar, I've got S. I'm using regular letters. That's sample. If I'm doing a population, I'm going to do the same calculation. I'm just going to replace the letters with Greeks. and I'm going to replace my sample with a population. This calculation is a pain in the neck to do by hand. It is possible, but it is not trivial. I do notice there's one major additional difference between the formula on the left and the formula on the right. Other than replacing little n with capital N and replacing my Roman letters with Greek letters, what else is different between those two?
Don't subtract one from the population.
So why the hell do I do it in the sample? A mathematician by the name of Bessel said, hey, populations are assumed to be big. They're complete. But when you do a sample, you don't know if you're getting a good distribution in that sample. Felix?
Is it also connected to the infinite thing we had in the homework?
Yeah, the effective infinite. Yes, it's connected to the effectively infinite. This is small, right? The population is assumed to be so big, it's effectively infinite. But this number is calculated from these numbers. You get X bar from all of the X's you gathered, right? Which means you've used those numbers once. And since you've used them once, you lose a little bit of freedom. It's literally called a degree of freedom. And so we take away that to give us a little more spread. Because when you divide by a smaller number, you get a bigger thing, right? So I give myself back that little edge. That n-1 is called Bessel's correction. And it's only used for sample as opposed to population because I had to calculate something from the same number. And I don't want to use this extra information twice. So take it away once. It's a weird idea. If I didn't do this, then S squared would underestimate sigma squared. So this makes them come closer together. It unbiases my estimator. Unbiased. Wait, remember we're trying to control bias. Talked about that in chapter 2. I lose this degree of independence. I undo it to account for that bias. These are squared. If I am looking at numbers that represent, I don't know, pull something out of thin air. Scores on the state exam, right? That was one of our data files. Then this number would be in points squared. Have you ever seen anybody look at your exam and go, hey, what's your square points? This doesn't make a damn bit of sense. I squared this. If I take the square root of these numbers are called variance. Variance, not like variants, like the Loki movie. No, wrong variant. How much does this vary? That's in squared. If I take the square root S or sigma without the square on it, Felix, that's my standard deviation. On page 112 is a complete calculation worksheet for an example. We figure out the difference between each number and the average. We square it and we add them up and divide and take the square root to get the standard deviation. I am not going to do this calculation by hand. But you should look at this on page 112, because that's the calculation I'm going to show you how to do automatically in 2 places, not just in Excel, on Monday. Square root of the variance. Thank you all. If you came in late, come give me your homework. We'll see you all on Monday.